In this example, there are two toboggans that are connected by a rope. The first toboggan has a mass of 60 kilograms and the second has a mass of 40 kilograms. The two toboggans are pulled by a rope connected to the first toboggan. If the force exerted on the rope is 250 newtons east and friction can be ignored, find A, the acceleration of the toboggans, and B, the tension in the rope connecting the toboggans. So this example is similar to the last one that had two blocks. And the most important thing to notice right away is both of these objects have the same acceleration, which means we can actually group them together as one object when we analyze it. And that can make our lives a little bit easier, especially if we're solving for something like the acceleration of both toboggans together. So in a problem like this, the first thing I like to do before I draw a free body diagram is I just want to sketch out what's going on. Here's toboggan 1. There's a rope connecting them. Here's toboggan 2. There's a little track. And then here's a rope that's pulling toboggan 1, and that's where the force is getting exerted. So that's 250 newtons east. So in this question, there's my x direction. I'm going to call this east. And that'll be my positive direction. And then here's my y direction, and I'll call up positive direction. So since I'm dealing again with two objects that have the same acceleration, when I draw my free body diagram, I'm going to lump them together. So for my free body diagram, I'm just going to call this big M. So that's both of the toboggans together. So because this is a frictionless surface, which is awfully nice, there's no friction. So the only force acting in the x direction is this force here, which is my applied force. There's obviously gravity, which will be acting on both sleds, both toboggans. And there's obviously a normal force, be acting on both toboggans, pushing it up. So since, again, there's no acceleration in the vertical direction, and I'm not asked to find the force of gravity or the normal force, I'm not going to write Newton's second law in the vertical direction for this question. If I wanted to, I could, but I don't really have to. I just know in the back of my head that the magnitude of the normal force is going to be equal to the magnitude of the force of gravity, so that there's no net force vertically and no acceleration vertically. What I will do is I'll write out Newton's second law in the x direction. So in this case, there is an acceleration. I don't know what it is, but I would like to find it. In my positive direction, the only force acting in the x direction is the applied force. That's in the positive direction. And that's going to be equal to the mass of both of the toboggans together times the acceleration of both of those toboggans. In this case, I'm not going to do that. That looks like there's another force acting on my toboggan. Let's try that again. I'm just going to draw a little side note. M is equal to the mass of toboggan 1 plus the mass of toboggan 2, which in this case is 100 kilograms, 60 plus 40. I'll use that information over here. Acceleration is equal to the applied force over the mass of both of those toboggans together. The applied force was 250 newtons with 3 significant figures. My mass is 100 kilograms with actually 4 significant figures. So my final answer, the acceleration, is also going to have 3 significant figures. So my acceleration is going to be 2.5 meters per second squared east. So that was a pretty straightforward way of figuring out the acceleration of two toboggans simply by lumping them together. So that was actually the solution. Now for B, I need the tension in the rope connecting the toboggans. So I'll go back to my original picture. I want the tension here. I can't solve for the tension by analyzing this free body diagram, because in this free body diagram, the tension is internal. So if I want to figure out the tension between these two toboggans, I'm going to have to choose one of them to draw a free body diagram for separately. It doesn't matter which one you choose because you can solve it very easily either way. I'm going to draw the free body diagram for toboggan 2 simply because there are fewer horizontal forces involved. And why should I do more steps than I have to? So here's toboggan 2. I'll call that M2. In this case, the second toboggan was 40 kilograms. There's a normal force acting on toboggan 2. There's a force of gravity acting on toboggan 2. And there's this tension force. I'm just going to call that T for tension in the rope that's connecting toboggan 1 and toboggan 2. I'm going to write Newton's second law in the x direction. F net in the x direction is equal to the mass of toboggan 2 times the acceleration. Because I chose a really easy free body diagram, there's only one force in the x direction, which is tension. That's equal to m2 times the acceleration of that toboggan. m2 was 40 kilograms. The acceleration was 2.5 meters per second squared, which means my tension will be 100 newtons with 3 significant figures. So when I write my final answer, I'll write, therefore, the tension in the rope is, and I'll write it in scientific notation just to be perfectly clear how many significant figures I'm dealing with. So 100 newtons.